Don't know the answer? Ask the Naked Scientists.
Hello, welcome to this week's edition of Ask the Naked Scientists with Dave Ansell and with me, Matt Jamison. We're going to start this session with a story, though. The airwaves are yours.
I don't know if you've ever had the problem, you're almost in the middle of nowhere and your mobile phone doesn't quite have enough reception.
Yeah, and you have to sort of chase the reception, don't you?
Well, some researchers in Rice University in the States, a guy called Lin Zong and some of his colleagues have come up with an idea or implemented an idea which might improve this. Instead of just having one antenna on your phone, you have two. And you design them so that one will point in one direction and the other one will point in the other direction. Because at the moment, mobile phone antennas emit radio waves in all directions really quite efficiently.
Right.
And almost all of that energy is just going off in random directions, doesn't end up at the base station. So if you can have more antennas, which will sort of shoot beams of something a bit like a beam, although it wouldn't be a very tight beam, towards the antenna you're talking, the mobile phone mast you're talking to.
See, when you said beams there, it sounded very Thunderbirds for a second.
With only two antennae, they'd kind of be more like kind of just pointing all of your radio waves in one direction rather than the other direction. And so it should use either half as much energy or you get twice as much power so you should be able to get further away from your phone mast and still get good reception.
That would be very handy. Because there are those times, aren't there, when you're in, for example, my in-laws live in deepest Wales, and the amount of times I'm hanging out of a window trying to send a text or something, it can be quite dangerous.
Yeah, my parents live in Devon.
Yeah.
They just don't have it. There's no reception.
No.
You have to climb. It's quite good for exercise.
Yeah.
You have to walk up a hill in order to be able to talk to any of your mates.
We have some weird and wonderful questions, including this coming in from Paul Anderson. Should bridges be built with floats and propellers?
Yeah, I think he's got a interesting idea. His idea is that at the moment all of these bridges are being washed away in Pakistan.
Yeah.
And so what he thought was, why not build the bridge kind of on a boat, and then the boat's got propellers on it, so that if it gets washed away, it can just sort of use its propellers to drive its way up against the flow, and it will stay in one place.
But it would have to kind of propel sideways, wouldn't it? Because
you sort of have boats pointing up the stream.
Yeah.
And that sort of, instead of having piers, it's actually, it's an ancient form of bridge technology, actually. It's called a pontoon bridge. The Romans were certainly building them. I think they built one across the Rhine in about a week or something scary, Julius Caesar. And you just kind of build your bridge on boats.
Had to get those straight roads, didn't they?
They did. They were incredible, the Roman army.
So would that actually work, do you think?
I think it would certainly work for a temporary bridge. I think you'd have to keep filling it full of diesel to run the engines if you wanted to keep it running all the year round. And
Might
not
have a particularly good carbon footprint, might it?
and if your engine broke down, then you'd have trouble with your bridge as it slowly sort of floated off down the river. But certainly,
with cars on it.
Pontoon bridges are probably something they'll be using for temporary bridges in Pakistan at the moment. And powering them would mean they'd be able to survive in higher flows of the river, because otherwise they'd have a tendency to wash downstream. But for anything which is going to last a long time, I think it's going to get expensive in fuel, if nothing else.
We'll go on to this one from Elvira. It says, does alcohol used in cooking all evaporate?
I think most of it will do, because the alcohol boils at about 60 or 70 degrees centigrade, somewhere around there. And I think it's near 70 or 80. And so it's going to evaporate quicker than the water. Won't mean it all evaporates immediately, but it's going to evaporate pretty quickly. And if you cook something for 10, 20 minutes, pretty much the alcohol is going to evaporate off far quicker. Of course, this is how you make things like spirits, because the alcohol evaporates more quickly. You can then condense that stuff which is evaporating off, and it's much more concentrated alcohol, which then people enjoy drinking.
Now, we're not sure where this one's from. It could be anywhere. It comes in from Amanda Shantz. It says, could you build a weight-sensitive taser fence? Now, we have taser guns in this country, don't we?
Yes.
We don't. Do we have taser fences, or are you talking about electric fence?
I guess it's really an electric fence, isn't it? So I'm trying to work out why you'd want to do that. I guess it's you're trying to avoid electrocuting small animals or children or dogs or something. Yeah,
possibly. I can't really answer for Amanda, but I'm sure there's some logic in there somewhere.
It would be quite difficult to do because you'd have to have somewhere weighing the object which was touching the fence. So unless it was a fence which people climbed, you could make a sort of a fence which would only electrocute something if something heavy was hanging on it. and they were
Above a
touching it
certain
above
weight.
a certain weight, then you could probably do it. Weighing someone who's just sort of standing next to the fence and then is touching it would mean you have to have some kind of weight sensors all the way around the base of your fence, which is getting quite difficult. You'd also have to split up the weight sensors into small enough lumps that, you know, if you get two small children standing next to each other, they don't count as an adult and then electrocute themselves. It would be challenging. Engineers have managed to get around more challenging problems than that. I think it would be really why you would want to do it and who's paying for it. See no fundamental reason why it wouldn't work, but I think it might be expensive.
But check with your local police before trying.
I think
It's possibly the good answer. Thank you, Amanda, for that. Got one here. Comes in from Roland, who says, I was looking at the moon over a clear Cape Town morning the other day, around 10 o'clock, and started to wonder if the people in, say, Wellington, New Zealand could be possibly watching the night sky, moonlight at the very same time, taking into account the time difference. Is this at all possible? So I guess his kind of question is, how big an area of Earth can see the moon at one time?
It's pretty much the same question as how big an area of the Earth can see the sun at one time, which is essentially what part of the Earth is it in daytime. Because then anyone who can see the sun is in daytime. So it's essentially the half of the Earth which is pointing towards the sun can see the sun in daytime, and similarly the half of the Earth pointing towards the moon can, in theory, see the moon. If the moon is in the direction of the sun, so if the moon's up during daytime, it's very, very hard to see because the back of the moon is in shadow, so it's very dark. And also the sky is very bright because it's got full sunlight on it, so it's quite hard to see the moon when it's towards the sun. But if it's at 45 degrees, basically half the Earth should be able to see it with varying clarity. Possibly a little bit more around the edge because you might be able to see it from just over the edge.
I was going to say, is it then possible that the half of the Earth that can actually see the sun might have different levels of brightness because of the shape of the Earth? Or is the sun high enough so that everyone gets the same illumination?
If there was no atmosphere, the sun would look the same brightness to everyone if they're looking straight at it. It would still burn your eyes. But because if you're near sunrise or sunset, the sunlight's got to go through a lot more atmosphere. And the atmosphere tends to scatter out quite a lot of light. So what gets through to you is much dimmer, which is why it doesn't hurt to look at the sun just as it's setting.
You see, that is a great stat. I love that. That's why you can watch the sunset.
Yeah.
And rise, is it the same
thing,
principle?
because the sun is just grazing across the top of the atmosphere. And also blue light tends to scatter out more than red, which is why the sky is blue. Right. And so red light carries on through all this thick atmosphere, which is the reason why the sunset is red.
We've got Mark in Dunsford on the line. Good evening to you, Mark.
Good evening, Dr. Matt.
Dr. Matt? No,
Dr.
I'm not a
Matt
doctor.
and Dr. Dave.
I'm a doctor of nothing. You're through to Dr. Dave. What's your question?
The question I wanted to ask you was, the thing I can't understand about space is when they talk about explosions, when you get a detonation on Earth, you get fragmentation, and things just keep on flying until they lose velocity and power, and then they drop. But in space, why do when these stars go off, I mean, they're supposed to go off like, atomic explosions. Do they create their own sort of gravity by swirling the gases, or the gas is heavier? Do they draw matter back in? This is what I can't understand about gases. I just thought the particles, once they woof, they just keep on travelling and travelling.
Well, I mean, if you're actually in a vacuum in space and there's nothing else nearby you, then there's no forces on you at all. So if something gives you a push, you'll keep on going at that speed forever. And so if a star explodes, and if the bits have got enough energy to escape the star's own gravity, there's nothing to stop them carrying on and on and on until they hit something else. In fact, you're made up of bits of an exploded star.
Yeah.
Because all of the elements which are heavier than about lithium, I think, which is one of the really light elements, is sort of hydrogen, helium, and a bit of lithium, were made in the Big Bang in the first place. Everything else has been made in stars. And the stuff how it's got out of the star is in one of these big explosions in a supernova. And so all of the hydrogen, not the hydrogen, but all the oxygen, all of the calcium, all the metals, virtually the whole of your body, apart from hydrogen, was made in these supernovae. Because when they blow up, if there's enough energy there, the stuff will carry on travelling until they hit some other gas and slow down, condense a bit, and then somewhere else some other gas might condense and start forming another star. and some of the random dregs, the heavy dregs, which is orbiting around it, slowly form planets and eventually possibly life.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast.
We've got a email here from Rishikesh that says, will a piece of ice melt if kept in space where there is vacuum and the ice is not in contact with any other substance?
I guess the first question is where the ice is will depend on what's happening.
Whereabouts in space?
Yeah, because if you're in space, it might not be touching anything, but you're near the sun, then there's going to be sunlight sort of landing on this lump of ice, and that's going to heat it up. As it heats up, probably it's not going to melt. What's going to happen is as it heats up, the little molecules are going to just go straight into the gas phase. They're just going to escape and not come back again. So it will what's called sublime. Carbon dioxide does the same thing. It sort of just goes straight from a solid to a gas. And ice will just go in space, will just go straight from a solid to a gas, if it's close enough to the sun to do that. If you're a long way away, if you're out somewhere like Jupiter or the other ice giant, gas giants out there beyond Mars, then it's cold enough that it will mostly just stay as a solid. It will probably evaporate very, very, very slowly, but far too slow for you to notice.
There you are. I hope that's answered your question.
The rings of Saturn are made up of little lumps of ice, lots of it.
Got another email here, comes in from Vidya. It says, how do we measure the distance between 2 points on the globe? And I always wonder this, when you get to those crazy signposts that say London 84 miles and Cambridge 14 miles, how do we actually measure that?
These days it's easy, you just wander around with the GPS and you do a little bit of maths and the answer comes out. But originally it was a very, very difficult problem. And it was only even marginally solved in about the sort of 1700s. For a long time, if you know how big the Earth is, basically the question is sort of what your longitude and latitude. If you know the longitude and latitude of two places, you can then do some maths and work out how far it is between the two. In fact, there was a very good estimate of how big the Earth was by a Greek gentleman living in Egypt in about 200 AD, who looked at how measured the distance between two wells, which were both vertical.
Was one in Greece and one in Egypt?
I think there were two different places in Egypt because he had to measure the distance with like a wheel or a bit of string in between the two, so they were about 50 or 60 miles apart. And then he looked at the difference in angle the sun at midday was in the two wells on the same day. And from that, you can work out how much of the Earth you've gone, but in those number of miles you've measured, and then you can work out how big the Earth is. And he'd actually got a very accurate, really quite accurate result from that, more accurate than the French who tried it in the early 19th century when they invented the meter.
How does a satellite, which is essentially what GPS is, isn't it? How does that know the distance?
All the distances are measured from the satellite by radio waves, and radio waves travel at 300,000 kilometres every second. But the electronics in GPS is so good that they can measure differences in the times of travel. And so the American military work out where the satellites are they know 2 or 3 places in America and they know exactly where those are, and then they work out the time it takes from the message from the satellite to get to those 2 or 3 places. That means the differences in distances between those, and you work out where the satellite is. And then if you've got if you can see 5 or 6 different satellites, you know where all of those are. From the difference in distances, you can work out where you are. It's all geometry, really. And yeah, I mean, it was really easy now, but yeah, originally they had to do it using sextants and working out how high the sun is and what time midday was. And you could only do that once you had a clock which could keep time from one side of the Earth to the other. So working out how far east and west you were is very difficult. And until a guy called Harrison built a very, very accurate chronometer.
Have you seen this question from Jill? Why is it that when we put deodorant on, it takes our odour away?
I mean, there's a couple of things which deodorant does. One of them is that it sort of covers up the smell a bit by covering it up with a different smell. Another one is that they put ammonium chloride in there, and various things which can change the acidity, which affects the bugs which eat your sweat and make the smells. So if you can get different bugs living in there by changing acidity, changing the pH, you can get different things to go. And I think they are now actually also adding things in there which actually stop you sweating, either by blocking up the pores or by just kind of chemically affecting. Is
that healthy though?
I don't know.
Is it healthy to block up a sweat?
Sort of stop you sweating. I'm guessing you're sweating. It's a good. I guess might slightly increase your chance of overheating in general. But your body's quite. I mean, unless you're really, really stressed on a very, very thermally stressed on a really hot day, I imagine it's not going to make a huge difference because your body's very good at kind of pumping blood somewhere else where it can lose the heat. I mean, it's much less an effect thermally than putting on a jumper or something.
Dave from Norfolk has been on the email saying, officially, no good evening, he's straight in here. Officially, the High Frequency Auroral Research Programme is an ionospheric research programme, but surely sending up 1 billion watts of high-power radio frequency into the atmosphere could have dire consequences on the weather or even the potential to cause earthquakes. What use does this research have? And before you answer that, can you explain to us what on earth he's on about?
I can do my best. If you go up in the atmosphere, so if you go higher and higher and higher, the air gets thinner and thinner and thinner. And then when you get very high up, you get to a region where it's being bombarded by particles from the sun, lots of ultraviolet light from the sun, and most of the atoms are missing electrons. So some of the electrons get knocked off the atoms, and this means you get the electrons can move around and the atoms can move around, and it will conduct electricity. It's very, very tenuous up there, but it will conduct electricity, so you can get big electric currents flowing through it, and it will interfere and do interesting things to radio waves. It's the reason why people can listen to shortwave radio from thousands of miles away. Because the radio waves bounce off this ionosphere instead of going off into space like they should do. They bounce off the ionosphere and come back down again, bounce off the ground and bounce off the ionosphere. And so you can be sitting here and listen to radio from, I don't know, Cape Town or something. So this is the ionosphere. I think what the Americans are doing there is attempting to play with the ionosphere in order to change its properties, in order to improve radio signals going past, because during the day the radio signals can be very bad because the sun heats it up, and especially sunset and sunrise, because suddenly the amount of energy going into it changes hugely, and so it will change shape, and all of a sudden the radio propagation becomes rubbish. And so they want to be able to affect its properties either for sending radio out or, I think more importantly, so that their radars work properly or predictably. So they're attempting to send heat it up using radio waves and alter its properties. And they're basically doing research on see how they're doing this. They're not using quite as much power as I think Dave was saying. Apparently they're sort of using a few megawatts, so 3 or 4 megawatts rather than gigawatts. I mean, it's about the same amount of energy as comes from the sun and lands on the Earth in about a 30 square metre, an area about 30 metres square. So compared to the energy coming from the sun, it's not immense. But then again, not very little of that energy will be absorbed up there. So it will change things, and they're attempting to change things. It could conceivably have an effect on the weather, but I mean, I have no idea what it would be. But it's unlikely to have a huge effect on the weather, and that, I don't know how well the ionosphere and the lower levels are interact with each other. I doubt it's very, very strongly. So it might have a bit of an effect, but they've been doing it for 20 years and nothing too bad that we know of has happened, as far as we know.
That's it for this week. Thanks for listening. Remember, you can send The Naked Scientists your questions by email. chris@thenakedscientists.com is the address to write to. And if you want to find out more about The Naked Scientists, then drop by our website, nakedscientists.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.